Hey guys, page 13. We started talking about the test for concavity. Did we get through all of example 1 on the bottom of the page? We did? Okay. So let me just do a quick recap from the bottom of page 13. So we talked about how if I want to do anything with the curvature of the graph, I have to go all the way down to the second derivative function. So we start off by finding f prime. And then we work our way down to f double prime. And this is where we're going to get all the information from the second derivative function. Okay, so once we get to the second derivative function, we set equal to 0 to find our critical points. So we factored out a negative 10x. We solved for x, we got 0 and plus or minus 1/2. And then we went ahead and we placed them all onto the second derivative sign line. And then once we have our initial critical points all filled out, now we want to test the intervals. So we choose values in each subinterval. I chose -1, -1/4, +1/4, and 1. And they all get inserted into the factored form of your second derivative function. And all you care about is to figure out whether it's positive or negative in that subinterval. So if I plug -1 in, I got a positive sign, which means that my first subinterval was going to represent concave up. So this full interval, the graph will look like as if it's part of a parabola that's opening up. If I plug in -1/4, I get a negative interval, so that means concave down. And then I plugged in 1/4, I got a positive interval, a positive sign, and then plugged in 1, and I got a negative second derivative value. So and then after that, we don't care about these test points, right? So you cross out the -1, -1/4, the 1/4, and 1. They're not going to play a role at all when you write your interval statement. Okay, so now we can write our statements. Concave up for the interval from -infinity to -1/2, and from 0 to 1/2. And then you have to be able to write out your because statements because f double prime is greater than 0. So I'll be looking for that on the quiz. Make sure that I will specify on the quiz to write because statements. Okay, so read your directions and make sure you understand how to write all these down. Okay, concave down will be my two subintervals here from -1/2 to 0, and then from 1/2 to infinity. Because f double prime is less than 0. Yes.
What if f double prime is 0?
Okay, if f double prime is 0, then what that means is that it could be a point of inflection. It could be that transition point from one concavity to the other. So for instance, f double prime is going to be 0 at -1/2, 0, and 1/2. And not only that, there's a change in sign at these subintervals, at these critical points. So that means we have 3 points of inflection. So 3 points of inflection at -1/2, 0, and 1/2. And the reasoning is because f double prime changes signs. It's not like relative max and relative min, where you have to say sign changes from positive to negative or from negative to positive. As long as you indicate that there's a change in sign, that's enough for a point of inflection. And also, what do these values mean? How did I find that -0.146, the 0, and the 0.146? Yeah, plugging the x value back into the original. Yeah. So the notations look the same, but these are ordered pairs. But the notations for concave up, concave down, those are intervals in terms of x. Okay. So they all use parentheses, but I'll make sure that we understand these are ordered pairs. These are x intervals. Okay, let's get some more practice with this on the quiz review, but do these steps make sense? All right, so you're doing the same procedure as first derivative test. It's just that with the test for concavity, everything's at the second derivative level, and everything means something a little bit different. Instead of Positive meaning increasing, now positive means concave up. Because we're pulling information from a different derivative. Okay, so we call this procedure test for concavity when we go through the second derivative sign line. I want us to briefly go over the last topic, which is called the second derivative test. And, this looks like something that would be called the second derivative test, but the second derivative test is named for something else. Okay, so we'll talk about that on the next page. Okay, so page 14. So the second derivative test, that name is meant for us, is a test for relative extrema. It's a test for relative max and relative min, and it's not a test for point of inflection. So what we just got done doing on the previous page is called test for concavity. So the second derivative test finds relative max and relative min. And if you're thinking, wait, don't we already have that? Don't we already have the first derivative test? And we do. So the second derivative test does the same thing as the first derivative test. It just uses different method to find the relative max, relative min. And as you can guess, it's using the second derivative function to help us get there. Okay. So I just want us to kind of explore something here. So I want you guys to draw this out here. Draw a parabola that's opening up. And let's say I label this order pair as 1, -4. What would you say f prime of 1 is equal to? Well, that's f of 1. Yeah, f prime of 1 is equal to 0 because why? Slope is 0. Okay, so that's a relative minimum, right? That's a relative min. Slope is 0. Now, what about the second derivative at 1? Okay, second derivative is talking about concavity. Now, this point here is part of a what? Concave up or concave down? Concave up. So maybe this could be equal to 5. But either way, it could be 6, it could be 10, it could be 11. But either way, it's going to be greater than 0. Okay. I'm just putting 5 there as an example. So this is what I want us to understand here is that since f of x is concave up, and slope is equal to 0, there must be a relative minimum at x equals 1. So that's the conclusion that we can make, because if you combine slope 0 and concave up, there's no choice but for that point to be a relative minimum. Does that make sense? Okay. So likewise, let's say I have another graph that looks like this. And let's say I have an order pair here at 4, 8. Okay. What would you say f prime of 4 is equal to? Also 0, right? That's a slope 0. But the difference here is, right, the concavity is different, right? F double prime of 4, what would you expect out of this? To be less than 0, right? So maybe this is -9. I'm just choosing, it could be any number less than 0, right? So if you see a negative concavity value, that means the graph is concave down. So since the graph is concave down, and slope is 0, there must be a relative max at x equals 1. Sorry, x equals 4. So if I pair slope 0 and negative concavity value and the fact that it's concave down, I must be achieving relative maximum. Okay. Does everything make sense so far? Okay, now here's where students make mistakes, okay? And I want to kind of bring this up to you so that you're aware of it and that you can avoid it. So the issue is that when students see that +5, the tendency is they think positive must mean it's greater than 0, must mean relative maximum. So it's easy to look at that 5 and think, okay, that must be a relative max, because that's a relatively big number compared to, you know, positive versus negative. So they associate positive with maximum, but that's not the case. You want to associate positive with concave up, and if you can see concave up on a graph, you're going to be convinced that it's a relative minimum. So it does feel a little bit backwards here that a positive second derivative value is going to lead to a relative minimum. But the reason why is because we're calling that a concave up graph. Likewise, when you see a negative value, you're going to want to associate a negative with a relative minimum. But what you want to do is you want to say a negative means concave down, and concave down is going to lead me to a relative maximum. So just be aware that it's easy for students to make mistakes because we associate positive with max and negative with minimum. That's just natural, right? Okay, so now that we understand that process, let's talk about this procedure called second derivative test. Okay, so I'm going to jump directly to example 2 and kind of show you the steps. Okay, so example 2 says find the relative extrema of the function. So I want to find relative max, relative min, but I don't want to go through slope sine line. So first things first, let's find f prime. Okay. Go through power rule. Now, relative extrema, relative max, relative min comes from the first derivative function. So we're still going to follow the same process. We're still going to set f prime equal to 0 because we're going to be looking in the same place. It's just that we're not going to create a slope sine line after this. Okay. I can go through trinomial factoring. I can do star method. A times C, sorry, 8. Multiplies to be -9, adds up to be -8. My A value is 33. So multiplies to be -9, adds up to be -8. It's going to be -9 and 1. Okay. I take those two fractions, I put them into my factored form. Reduce if I can. 9/3 reduced to be -3. Okay. Push the denominator out in front of the x. And now we can solve for x. My critical points are 3 and -1/3. So these are my candidates for relative max, relative min. But I'm not going to do a slope sine line, because if I do a slope sine line, then that's the first derivative test. We're going to go in a different direction from here. Okay. Everybody good so far? Okay. So we have our candidates for relative max, relative min, but we're not going to do the first derivative test. We're going to do something here called the second derivative test. So now what we're going to do is we're going to find the second derivative function. Okay. So f double prime. All right, 3x squared becomes 6x. -8x becomes -8. Okay, we have the second derivative function. Now, we're not going to set this equal to 0, because if we set this equal to 0, then we're doing test for concavity, right? Then we're doing vertical points of inflection. We don't want to do that. What we want to do is we want to insert these values into the second derivative function. Okay, and that's the second derivative test. This is going to help us decide what's happening at 3 and -1/3, whether there's a relative max or a relative min. Okay, so one at a time, I'm going to insert these candidates from first derivative into the second derivative function. So insert 3 in for x. 6 times 3 minus 8. What does that equal to? 10. Okay. So the number is not that important. It's the fact that it's what? Positive, that is greater than 0. Okay, so let's verbalize this. If the second derivative is greater than 0, that must mean the graph is part of a what? Concave up. And if you can say the words concave up, and if you can draw the picture that represents concave up, you'll be convinced that you're staring at a what? Relative minimum. Good. So you'll say relative minimum. That is the second derivative test. Now, we would get the same thing if we were to create a slope sine line at 3. Okay. And we would arrive at the same result. But we're practicing the second derivative test. Sorry, minimum. So this it's going to be increase followed by increase. We will get the same result. All right, so likewise, we're going to test out negative 1/3, see what's happening, but we're doing this without the slope sine line. We're using the second derivative function. So negative 1/3 in for my x's, get 6 times negative 1/3 minus 8. Negative 2 minus 8, what's that equal to? Negative 10. Right? It's just a coincidence that one's positive and the other's negative, but the numbers is not that important. But it's a fact that is what? It's less than 0. Okay, so let's verbalize it. This graph is part of a concave down. You can draw a graph that represents concave down, you'll be convinced that you're staring at a relative what? X. If you don't verbalize it and draw it out, the tendency is that you're going to make a mistake because you're going to see that positive and you're going to associate positive with max and you're going to associate negative with minimum, and that's where student mistakes occur. So the common question that students ask is, why do we need this, right? Because if I have the first derivative test, I'm always going to use the first derivative test. That's just natural. This feels like a kind of a convoluted way of getting to my conclusion. But on the AP exam, sometimes they force you to arrive at your conclusion using the second derivative test because the first derivative test would not be sufficient. So let me kind of show you what that looks like on the AP exam problem where they're forcing you to make a conclusion based off the second derivative test. You can find space. This won't take a lot of space, so you can either find space on a separate sheet or you can kind of just follow along. Now, here's an example. Let's say f of 2 is equal to 6, f prime of 2 is equal to 0, and f double prime of 2 is equal to, and that's all the problem gave you. We can't do the first derivative test because we can't create a sine line because there's not enough information. But the problem could ask you, okay, what conclusion can you make about what's happening at x equals 2? Well, let's reason this out here. F prime of 2 equals 0, that means there's a slope of 0. But f double prime of 2 is equal to 12. That means that at 2, the graph is what? Concave up. And if I pair slope 0 with concave up, the only conclusion that I can make is that there must be a what? Relative minimum. Must be a relative minimum at 2.6. And this is what AP exam multiple choice question could look like, testing students on their knowledge of using the second derivative test. Okay. Likewise, if I do f of 4 is equal to 3, f prime of 4 is equal to 0, and f double prime of 4 is equal to negative 29. Again, slope 0, but now what can I conclude here? Negative concavity, that must mean it's concave down. And if you can visualize concave down, you can convince yourself that there must be a what? Relative max. If the slope wasn't 0, then the second derivative test would not apply. We're only dealing, we're able only to make this conclusion if it's part of a slope 0, right? If it's not slope 0, then it can't be a relative max. I mean, it could be, but we wouldn't be using this test. Okay, any questions? It's not hard, but you can see how students can mix those up, and I just want to point that out, why it's easy to mix these two things up. Okay. As we turn to page 15, 15 through 19, these are summaries of the theorems and the topics that we've done. So I have a summary sheet for extreme value theorem. I have a summary sheet for mean value theorem, for Rolle's theorem, first derivative test, test for concavity, which we just did, and then the second derivative test, which is testing for max and min using the second derivative. So what I want to briefly do is I want to just run through extreme value theorem, since we haven't seen that in a while, and then we can start our quiz review worksheet packet. Okay, so the whole point of extreme value theorem is to find the highest and lowest point on a closed interval. So the first thing we have to establish is the graph continuous on the closed interval? If there is a denominator within your function, you're always going to have to set that equal to 0 and make sure you can find the asymptote and make sure the asymptote is not interfering with your interval. If your asymptote doesn't interfere with the interval, then you're safe. You can write your statement and move on. But if your asymptote lands somewhere inside your interval, then you just have to stop the problem and say the function is not continuous, extreme value theorem does not apply. Okay. But let's say the function is continuous, okay? Then we'll make sure that we have to write out our conditions, okay? And make sure that I will specify on the quiz, specify and write out your conditions, okay? That's part of your, to earn full credit. Next step, find critical points. Okay, so how do we find critical points? We find f prime, and we set the numerator and the denominator equal to 0 if there's a denominator. Okay, if there's no denominator, then we can just focus on the numerator. Okay, we set the so we set both equal to 0, and we find our critical points. But what do we have to be aware of with the critical points? Are we going to test every critical point that we find? Only the ones in between the interval, right? So if you don't find any critical points, that's okay. That means you're only going to test 2 endpoints. But if you do have additional critical points, you're going to test your critical point and your endpoint. And where did they go? They all go into the original function, and then you just compare their y values. Okay, highest y value is your absolute max, lowest y value is your absolute min, and I only care about the y values. Okay, so let's go to our worksheet 1, and let's try number 1. Okay, number 1 is only asking you for critical numbers, so just find f prime and set f prime equal to 0, and that's it. Okay, so try number 1. Okay, factor using star method, if that works for you. Multiplies to be 15, adds it to be -8. Reduce if possible. If you can't reduce, pull the denominator in front of the x. Set your derivative equal to 0. There's only two critical points, 5/3 and 1. That's all it's asking for number 1, find the critical points. Okay, number 2, find the absolute extrema. So now we got to apply extreme value theorem. First, the only condition that's required is continuity. Is there going to be issue with continuity? No. All right, there's no denominator. It's a polynomial. Our function is continuous, but make sure that you're writing out your condition, and then also you're specifying the interval. If you just say the function is continuous, that's not good enough. You got to say continuous on the closed interval. Okay. We're definitely testing the endpoints. The endpoints are definitely candidates, but we also need to find critical points. Where do critical points come from? Find the derivative and set equal to 0. In this case, there's no denominator, so you're only going to set the numerator equal to of the derivative equal to 0. Okay, so I have two critical points. What do we need to do to make sure that those are valid critical points? Interval, yeah. So does 2 fall inside the interval? Yes. Okay, does -1 fall inside the interval? Yes. So we're going to test 2 critical points and 2 endpoints. All 4 points will be tested. How do we test them? They all go back into the original. Okay. Okay, on Tuesday, you will get to use your calculator. And I only care about the y value. So absolute max is 8. Absolute min is -19. That's it. Okay, number 3. Number 3 is Rolle's theorem. And Rolle's theorem is we want to guarantee a slope 0 somewhere on the interval. But before we do any of that, we have to go through a couple of conditions, right? So there's a continuity condition, but there's also a differentiability condition. 99% of the time, if it passed the first condition, it will also pass the second condition. But there could be an issue with the continuity here. What do we see about this function that we have to be aware of? That denominator. Yeah. That denominator has a variable, which means that there is a potential, there's a break in the graph, and that break could affect the interval. So How do I find that break? That equal to 0. X equals 0. That tells me that there's a vertical asymptote at x equals 0. Now, is that vertical asymptote going to interrupt my interval? Yes, right. It sits right in between my interval. It's going to, so I can't guarantee continuity because there's a vertical asymptote. So I say the function is not continuous. Therefore, Rolle's theorem doesn't apply. Okay, we're going to do number 4. Number 4 is going to take a little bit of space. If you can cross off number 5, because we're going to do a problem is similar to 5 for number 6. So 5 and 6 are kind of redundant. Cross off number 5, and we'll use the space for number 5 for 4. So 4 will take some time, some space here. Okay, we have a function, negative root 25 minus 5x on the interval from 3 to 5. Determine if mean value theorem applies. So the first thing is we want to determine, is there any issue with continuity or differentiability? I'm just going to do a quick test here. I want to make sure that 3 and 5 does exist on this function. So if I insert 3 in for x, 25 minus 15 is 10, root 10, that's safe, that's a real number. If I plug in 5, 25 minus 5 times 5, that's 25 minus 25, which is 0. Square root of 0 is also valid. That's fine. So our function is continuous, and if it's continuous, it'll also pass the differentiability test, at least the ones I give you. So just have to make sure that we write out our conditions. Our function is continuous. And our function is differentiable. Ensure that not only is there no breaks in the graph, that it's also a smooth curve. But make sure that you're using parentheses for differentiable statement and brackets for continuity statements. Okay, so our conditions passed. This is guaranteed now. We should be able to get mean value theorem to work. Now, the first thing that we do with mean value theorem is not the derivative. Okay. What's the first thing that we have to get information about? We want to find order pairs. So don't jump into the derivative just yet. We got to find order pairs because we got to find a slope. We're trying to figure out what is the goal of our process, right? We want to figure out what the goal is so that we can then ask the derivative to find the location of that goal. So first things first, let's find our order pairs. So no calculus yet. You're just gathering information from the function, getting the order pairs so they can get to the slope. So let's insert 3 into the function. (25 minus 15 is 10. 10 to the 1/2 is anything is square roots, so I'm going to change that to the square root, negative square root of 10. 5 into the function. 25 minus 25 is 0. Negative 0 to the 1/2 is the same thing as 0. Okay, so now that we have our order pairs, what do we want to do with them? We want to find the what? Slope. Find the slope, right? Because we want to guarantee a slope, so we first have to figure out what slope we're trying to guarantee. So this is the process of finding out what we want to guarantee. So here's our slope. Change in y over change in x. Okay, we'll set this off to the side. And then we're going to ask the derivative to tell us the location of that slope. But right now, we at least have our goal found, and we'll set that off to the side and we'll come back to it. Okay. Now the next thing is we're going to get to the derivative. Okay, so we're going to find the derivative. And after that, we can then involve the slope that we want to try to achieve. Now, if I want to find the derivative of this function, what do you think is required here? Chain rule, right? I got parentheses with messiness on the inside, with an exponent on the outside. I got to do outside and inside portion. Okay, so let's do the outside derivative first. So we go through power rule. Okay, so we go through power rule, bring down the 1/2, subtract 1 from the exponent, keep the inside intact. Okay, so now that we took care of the outside derivative, we're ready for the inside derivative. What's the inside derivative going to be? Yeah, and it goes in its own separate space. Make sure that you don't put that -5 inside the parentheses. It's going to be to the right of expression. Okay, let's clean this up here because we're basically doing this. We're just setting the derivative equal to our slope, and then we're looking for the location. Okay, I'll do some cleanup here. The negatives cancel out. The 5 goes up top. The 2 goes below, and the square root also goes below. So now we're just going to set our derivative equal to our slope. Put this up here. I want to make sure that we understand this process here. Okay, we're using the derivative function, and we're giving it the slope value, and in return, we want to find the location of that slope, right? So we're just using the derivative function to help us get the information that we want. We know what slope we want, but we're asking the derivative to help find us the location where we're guaranteed where we know the slope is going to occur somewhere along that curve. Okay, I'll cross multiply here. I'll divide by 2 just to get that 2 and 5 to combine. Okay, it looks messy, but an easy way to get rid of the square root is I can just do what on both sides? The square both sides. And now I'm just trying to solve for x. That reduces all the way to 4.5. So that's our C value. So we know that when x is 4.5, and this is a guarantee here, is this nicely between our endpoints? Yes, and that's a guarantee, right? If we don't get that value between our endpoints, something went wrong. Okay, we should be able to always find the location somewhere between our interval. So we know that at 4.5, the graph is going to experience an exact slope of root 10 over 2, and mean value theorem, basically just using the derivative, allows us to guarantee it and also find the location where that behavior is going to occur. So again, with mean value theorem, state your conditions, find your order pairs, find the slope. So do all the non-calculus stuff first. And then once you have your goal set up, then you can find the derivative, set the derivative equal to your target slope, and then look for the location where that slope occurs. Okay. Okay, can we just do one more here? This is example 6. Use the first derivative test. So this one is easy. Find f prime, set f prime equal to 0, solve for x, make your sign line. Okay, so f prime is 3x squared minus 24x minus 27. Factor out 3, continue to do your trinomial factoring, and you'll get -1 and 9. So -1 and 9 goes directly onto your slope sign line. You can test -2, 0, and 10. They all go into your first derivative function. I get a positive, negative, and a positive. So I know that there must be a relative max at -1, must be a relative min at 9, and I just have to make those statements along with my because statements. Okay, number 7 is test for concavity. That should go pretty easily. Number 8 is second derivative test, which we just did, but we'll finish that up on Monday. And I haven't gone over the graphing on number 9, but that's what we can spend 5-10 minutes on that. And we'll continue reviewing Monday, your quiz, your test, your quiz is on Tuesday. I will have help sessions Monday morning at 7:30. Tuesday morning at 7:15. I'll send out a reminder. You can join on Teams. After I send out a reminder, I'll also record them as well. Okay, come and get your phones. You set the denominator of the. I should have played that. I don't know if I got it. Sorry, I thought that's necessary. Thank you, next to me. Thank you.
There's like sands like all over. Yeah.